Hello, dear learners. When you are attending a maths lesson with me, get ready with your pen, book, and your calculator. Today, we are going to do some exam questions. Exam questions involve grade 11 probability questions also. So, we start with the revision on that. Then, we go straight to the questions. In the last lesson, we finished doing everything in counting principles. Don't forget to check part 1, 2, 3 of counting principles, which is uploaded in my channel. Now, in revision, the three important formulae that you need to remember is number 1, if A and B are two independent events, probability of A and B is equal to PA times PB. That is, this A and B when A and B are independent events. But if A and B are mutually exclusive events, then probability of A or B equal to PA plus PB. So these are two formulae which is not in your formula sheet, but this last one is in a general formula for any two events A and B. PA or B equal to PA plus PB minus PA and B. So that is in the formula sheet. The other two you need to remember. So one is when two events are independent, the other one is when they are mutually exclusive. Okay, so you keep this in mind when you are doing problems. Another thing that we are going to do, the first question that I have taken from exam paper is a question with the contingency table. So first you must know what is a contingency table. A contingency table shows a count or number of observations grouped by specific characteristics. So it always shows the count, the total in the last column, in the last row, like this. This is the example of a contingency table. So here this table below shows the favorite spot for 120 learners. That means the total number here is 120. Now the meaning of this table is there are 70 boys in our sample space and 50 girls, and out of the boys 32 boys play golf, 18 boys play tennis, 20 play squash, 12 girls play golf, 23 play tennis, 15 play squash. So if you look at all those who play golf, the total is 44. All those who play tennis, including boys and girls, 41. All those who play squash, 35. So once again, the total is 120. So you must have an idea about what are all these numbers represented by. Now let's go to the question. Determine the probability that if a learner is selected at random, 4.1.1, the learner who is selected is a boy who plays tennis or squash. So the question is probability. So remember the formula for probability. Probability of any event. Probability of any event is equal to number of outcomes of the event divided by total number in the sample space. That is the probability of any event, or any all total number of outcomes in the denominator. So here the probability that if a learner is selected at random, a learner who is selected is a boy who play tennis or squash. So the probability of this event, probability of a boy playing tennis or squash, is equal to, look at the boys, how many of them play tennis or squash? So tennis there are 18 boys, squash there are 20 boys, so it's equal to 18 plus 20, or always stands for plus, over the total number in the sample space, which is 120. So here the answer is going to be, so just take the calculator and calculate the answer. The answer is going to be 19 over 60. You can also write the answer as a decimal, 0,32. That is answer for 4.1.1. Now, the determine the probability that Elena who plays tennis is selected. So here we are finding the probability of a boy who play Elena. No, it doesn't say boy or girl. A learner who play tennis. So what are the number of outcomes of the event here is playing tennis. How many learners play tennis? So there are 41 who play tennis. So the answer will be 41 over total number in the sample space, which is 120. You can leave the answer like that in the simplified form, or you can write the decimal, corresponding decimal, 0,34. Now 4.1.3, a learner who is a girl is selected. Determine the probability that a learner who is a girl is selected. So we are finding probability of a girl actually. The learner selected is a girl. What is the probability? So check how many girls are there. Girls in total there are 50 girls over total number in the sample space 120. Write the answer in the simplified form, or you write as a decimal. So it's 5 over 12, or you write as a decimal, which is 0,42. Now 4.2 are the events choosing golf as a favorite sport and being a boy independent. Okay, when the question is about independent, that's when you must remember the formula for independent events, which is not in the formula sheet. That is probability of A and B will be equal to PA times PB, which that is what we wrote in the beginning. If two events are independent, then PA and B equal to PA times PB. So we are going to use that formula in this question. Let's see how we use it. Okay, because here we have two events, choosing golf and being a boy. So we have to take the two, being a boy. Okay, let's see, and also choosing golf as the favorite event. These are the two events here. So we have to first find the probability of these two. Then we are going to check if probability of boy being a boy and playing golf. So in the place of A and B, here we have being a boy and playing golf. So we must find these three to check whether they satisfy that equation. Okay, what is the probability of being a boy? How many boys were there? There were 70 boys. So being a boy, the probability is 70 over 120. Being playing golf, we must go and see how many play golf. There are 44. learners who play golf. Now let's also find how many boys play golf. There are 32. Out of boys, only 32 play golf. We need that information here. So here it's how many play golf? There were 44 playing golf. 120. How many boys play golf? There were 32 boys who were playing golf. Now we are going to check if the equation is satisfied here. The equation says probability of boy multiplied by probability of playing golf equal to, so let's find it to see if it's equal to that. 70 over 120 times 44 over 120. What do we get here? We can always write this as a decimal to compare, which is going to be 0,21. Here also you find what is the probability of being a boy and playing golf. That will be equal to 32 over 120, which is 0,27. So what do you notice from these two now? Probability of being a boy and playing golf is 0,27, but when you multiply the product, it's 0, they are not equal. So this is how we are going to conclude now. 0,27 is not equal to 0,21. Therefore, they are not independent. That's our conclusion. So if you get the same values in these two, then you will say they are equal. That is probability of being a boy times probability of playing golf equal to probability of boy and golf. Then they are independent. Now they are not equal, so they are not independent. So the question says show all your calculation to support your answer. So these are the calculations that you show to support your answer. 4 marks. Okay. Now let's go to another question. The events A and B are independent, already given to you that A and B are independent. Value of PA and PB are also given. Determine PA and B. So we already know if A and B are independent, then PA and B will be equal to PA times PB. That is a formula of two independent events. So directly we can apply the formula. Therefore it's 0,4 multiplied by 0,5. So the answer is 0,2. So you get the 2 marks for knowing the formula, then getting the answer. Now PA or B. PA or B, we have this formula for PA or B. That is a general formula. PA plus PB, that is also in the formula sheet, minus PA and B. That is a formula. PA or B equal to PA plus PB minus B. So we have all this information now. PA is 0,4 plus PB is 0,5 minus PA and B we just now found it's 0,2. Therefore the final answer is 0,7. That is PA of B. Now we are going to see a 2.3 now. Let's say 2.3. 2.3. What is P not A and not B? not A and not B. Probability of not A and not B is actually it's 1 minus PA or B, everything except PA or B. But maybe some learners have a confusion about how to find that. Let me show you an easy way to remember how to find that. So in a Venn diagram, if you have A and B here, A and B. So if it says not A means everything outside A. That is called a not A. So you can shade everything outside A like this. So the part of B is also not A. So this is shows what I have shaded just now, shows not A. Now not B means everything out of B. So let me use a different shading to show everything out of B. This is everything out of B. So B here, everything outside B is not B. So not A, and if it was not A or not B, all this shaded, all the places that I have shaded is the answer. But here it's not A and not B. That means when both not A and not B. Do you see both means both shadings? In this case, both shading. I used a dots to shade not A. I used lines to shade not B. So where they are both these shades. So you can see both shades only in outside A or B. A or B. Okay, let me also mention what is A or B and A and B. For those who have forgotten, let me quickly mention what is A or B, A and B. A or B means this part, all in A like this. This is called A or A and B. A and B is only what you have in A and also in B, which is this one. This is A and B, where this is A and this is B. Okay. So now here the two shadings come everywhere except A or B. That means all A, B, outside part is A or B. So the answer to P not A not B is actually equal to 1 minus P A or B. Everything except A or B. That is the meaning of 1 minus. 1 minus PA or B means everything except you are subtracting A or B, probability of A or B from 1, because always the total probability of everything in the sample space is 1. 1 is the maximum probability. So 1 minus PA or B means everything except A or B. So we just now calculated what is A or B, which is 0, 0.7. So everything except A or B means 0, 0.3. That is the answer for 2.3. If you have any questions, write your questions in the comment box. Okay, now we are going to 6.1. I tried to include one question where you use the grade 11 and also the grade 12 probability. So this question has everything now. 6.1, PA is 3 over 8, PB is 1 over 4. Find PA or B if A and B are mutually exclusive events. Okay, so just now we found what is exclusive. How do we handle exclusive events? P, A or B, if they are exclusive, P, A or B equal to, okay, let me write here for now. P, A or B equal to P, A plus P, B. That is a formula we discussed in revision. So here this is equal to 3 over 8 plus 1 over 4. That was a direct question, that's why it only has 1 mark. So final answer is 5 over 8. Okay, now find P, A or B if A and B are independent events. Okay, what do we know if A and B are independent events? What we know is, okay, let me go back to space now. I think this space is not enough for us to write everything, so I'm going to answer it here now. Let me answer here, starting here. So I'm now answering 6.1.2. P, A or B if A and B are independent events. That's what I'm answering now. So we know that if A and B are independent events, P, A and B equal to P, A time and B equal to P, A times P, B. That's what you know. Therefore, here it's going to be 3 over 8 multiplied by 1 because that was given in the question, which is 3 over 32. We found what we know. We know if A and B are independent events, P, A and B is P, A times P, B. But the question is not to find P, A and B. The question is to find P, A or B. But there is a formula for finding P, A or B. P, A or B is P, A or B is equal to P, A plus P, B minus P, A and B. That was the general formula we learned. So we have everything in the right hand side. PA is 3 over 8 plus 1 over 4 minus 3 over 32. That was PA and B. So which is equal to 17 over 32. That is our final answer. Okay. Now we are going to see 6.2. It looks like, okay, it's not a counting simple question. Let's see what it is. 6.2. A car park has 14 Volkswagen cars and 18 BMWs. There are no other cars. Okay, so 18 plus 14, how many cars are there now? 32 cars. 14 VW, 18 BMW. Okay, during the afternoon, 2 cars are stolen. One early afternoon and the other later. Determine the probability that both cars were BMWs. Okay, so 2 cars were stolen. So it's not about arrangements or anything. So we have to, there are 2. So 2 cars are stolen. So the outcome must be 2 cars. So let's see how we can find the outcomes in this case. So 14 BMWs and 8 VWs and 8. So in this case, we can make use of a tree diagram. 6.2.1. We can start with the tree diagram here. There are 2 types of cars, VW and BMW. So the first car can be one of this. Now another car, 2 cars were stolen. So we must extend the tree diagram to one more branch, VW or BMW. Even if the first car was BMW, the second car stolen can still be VW or BMW. Now we are writing the outcomes. That means the two cars that are stolen can be VW, both VW. Here VW and BMW. First car VW and second one BMW, then BMW and VW, then BMW and BMW. So first question is, find the probability that the two cars are BMWs. 4 marks. Both cars are BMWs. So you already get a mark for drawing the tree diagram. Now we are finding the final probability, 2 BMWs. So which outcome shows 2 BMWs here? The last one. So we are actually finding the probability of 2 BMWs, that is probability of BMW, which is equal to, so now for us to write the probability, okay, the tree diagram is not finished without the probabilities marked there. So the probability of finding, okay, stealing a VW out of the 32 cars is 14 over 32 because there were 14 VW cars. The probability of stealing a BMW car out of 32 cars is 18 over 32 because there were 18 BMW cars. Now, this one, look at the next branch now. How many cars are now remaining? Because one car is already stolen. That means you are only left with 31 cars now. How many VWs are left? Because the first car stolen is one VW. So that means you are only left with the 13 VWs. How many BMWs are left if the first car stolen is VW? It's VW that is stolen, so all the BMWs are still left, but one car is gone already, so the denominator is 31. When we come to this branch, this shows first car stolen is BMW, so that means one car is already stolen, so the denominator is 31, but all the VWs are still there, so it's 14 over 31, and here it's going to be 17 over 31 because one BMW is stolen as the first car. So this probabilities of the second branch, very important. Denominators are only 31 because this branch shows the first car stolen. Second branch shows the second car stolen. Okay. Okay, now we look at the tree diagram to write the answer. First car BMW, the probability is 18 over 32 multiplied by second car also BMW, the probability is 17 over 31, which is equal to 153 over 496. You can leave it like this, but simplified form. Then you can also write the rounded off answer to 2 decimal place 0,31. That is 6.2.1. Now let's go and see what is 6.2.2. The first one stolen was a BMW and the second one a Volkswagen. Okay. So BMW, VW, that is our outcome. So let's look at the tree diagram. The outcome, the first one BMW, second one VW, that is out. So we just multiply these two branch. That's what we are going to do. Okay. So the question says probability of first one BMW and the second one VW, equal to first one BMW is 18 over 32 multiplied by second one VW is 14 over 31, which is equal to 63 over 248, which is 0,25 approximately, because these are rounded off answers. So that is answer for, that is actually the answer for 6.2.2. Okay. Okay, let's go to the next question, 6.3.1. Let's see what is the question now. Okay, question says 8 boys and 7 girls are to be seated randomly in a row. What is the probability? Do you see? When you see the word probability, you immediately underline and remind yourself that now you have to divide by the total number in the sample space divided by ns, because the probability formula I'm going to write it now. What is the probability that the row has a girl at each end? So total there are 8 boys, 7 girls. So total there are 15 children seated randomly in a row. What is the probability that the row has a girl at each end? So the restriction is only for each end. So let's go and see how we do this. So here we have 8 boys and 7 girls. So here the number of positions, there are 15. It's not easy for us to draw all the 15 positions. So let's draw only where there are restrictions. The first one must be a girl and the last one must also be a girl. So now there are other, how many positions are remaining in between now? 1, 2 gone out of 15. So there are 13 positions here that we haven't drawn. Okay, look at the first position. It must be a girl. How many choices do we have for the first position? 7, because there are 7 girls. How many choices do we have for the last position? We now only have 6 girls, because 1 girl is already seated here. So left with 6 girls. So 7 and 6. What about the middle now? There are 13 positions, no restrictions. That means they can sit in 13 factorial ways. So we are finding probability here. So let us write the number of outcomes of the event. That is what we were finding now. Number of outcomes of the event. Why are we writing this? Because we know probability of an event is equal to number of outcomes of the event divided by total number in the whole sample space. So we are now finding the number of outcome of the event, that is arrangement with the girls at each end, which is 7 times 13 factorial in the middle times 6. That is number of outcomes of the event. What is the total number in the sample space? That will be without any arrangement. Any boys and girls can sit anywhere. All the 15 children can sit in anyhow. That is 15 factorial. So probability of the event. What is the event here? Girl sitting at each end. This is our event. Is equal to, you don't really have to write all this. You can just say probability of the event equal to number of outcomes of the event, which is 7 times 13 factorial times 6 divided by 15 factorial. So now you can put this in the calculator. The calculator will give you 1 over what's the answer. These are common questions in the examination. But if you use the positions like this, it's easy to understand. Okay, let's go to 6.3.2 now. Let's go and see what is the question. The whole question was about a probability, so we need the NS for the next question also. Because the question beginning it says it's a probability. We are finding the probability here. Probability that the row has girls and boys sitting in alternate positions. Alternate positions, that is the situation here. Okay, let's go and see how they can sit in alternate positions. Now there are 8 boys and 7 girls. There are 8 boys and 7 girls. So because the number of boys and girls are not the same, the only way for them to sit is a boy first, then a girl, then boy, girl, like that, ending with a boy, because girls are one less than the boys. So this is the only way for them, because if you start with the girls, you will not end up with a girl, or you will not end up having all alternative positions. We saw it in another example in the previous lesson. So this is the only situation. So how do we, so the alternate positions are for boys. Now boys, how many boys are there? 8. Now this is a boy position, 7. The last one will be 1. That means all the boys can sit in A. So number, I'm now writing the number of outcomes of the event. All boys can sit in 8 factorial ways. Now we are coming to the girls position. This is boys position. This is girls. So girls can start by the first girl out of the 7. Then here it will be 6. Then like that. So here altogether they can sit in 7 factorial ways. Now total number in the whole sample space, that means anyhow the 15 children can write in 15 factorial ways. So probability of the event is equal to 8 factorial times 7 factorial divided by 15 factorial. When you put this in the calculator, you get 1 over 6, 4, 3, 5. That is the final answer. Okay. I think with that we are done with the exam questions. So by doing exam questions, we also revise the grade 11 probability. The important one is the independent events and exclusive events, and the one formula. Okay, I hope you understand. If you have any questions, put your questions in the comment box. Thank you for watching.